there is such thing as a positive linear operator, and positive linear operator, well, there is a definition behind that. So what is that? The positive linear operator, it is the linear operator which gives the positive number, positive non-negative number, I would say, for any vector v belonging to the space V. And so the fact is that P can also be written as T square, where T is actually a self-adjoint operator. But let's forget about this for a moment and try to prove the following theorem, the following problem. Let's assume that we have the orthonormal basis. I'm going to designate this as S. This is going to be orthonormal basis, which is by definition is the inner product of which is Kronecker symbol. It belongs to the space of basis of V. And well, in this basis, since these vectors are orthonormal, let's say these vectors are eigenvectors. So this is not just orthonormal basis, this is the orthonormal basis of eigenvectors. For some sort of linear operator P. And what does this operator have? This operator has eigenvalues, right? So consequently, the multiplication of P and Ui, that would be equal to, by definition, of lambda I Ui, where Ui belongs to eigenspace of eigenvector lambda I. And P is positive, given that P is positive, linear operator, P is positive. And so we are also given the operator T. And the operator T is, well, let's define it the following way. TVI, or we can say TUI in this case, defined as square root of lambda I Ui. And the problem asks us to prove that this is the positive self-adjoint operator, and this is the only self-adjoint positive operator defined this way. This is the only one positive linear operator. So the proof that T is positive self-adjoint. Well, if that's positive, then it is self-adjoint, but positive and self-adjoint. Every positive matrix is self-adjoint. Plus, it is the unique. We have to prove uniqueness. So let's get started with the first step. First, I'm going to show that this is a positive operator, because this is fundamental. We need to show that this is positive. For any vector V from the space V, a space of inner products, to be honest, we need to show that it could be complex space, it could be a real space, it doesn't matter. We need to show that this operator T is positive. So how can we show this? Well, first of all, we know that our basis is the basis of orthonormal vectors here. Then for any vector, it can be represented as the sum of, well, let's say alpha I, which is just scalar multiplier, and Vi. I'm going to say Ui because this is the vector from our orthonormal basis. This is the eigenvector, and I belongs to index set. And alpha I is a scalar multiplier which belongs to the field F. This is the field of our vector space. And well, this is by definition of linear algebra. Then our inner product v, what is that? It is essentially the sum of, sorry, this is the linear operator t, and we know this is linear operator, which is important. We're going to use it in the future. And v, which is, we can actually rewrite this as the sum. I belongs to I index set, alpha I scalar multiplier, and then ui, and again the summation alpha I and scalar multiplier and index set, blah blah blah, and then we have inner product. And then we can actually rewrite this expression and simplify that even further, which will give us the sum I of inner products like this. And then we have another sum here, which is the inner sum, again I, ui, and which can be again simplified as the sum I and j by two indices. And that would be like alpha, I forgot the alpha here, alpha I, alpha j conjugate, alpha I, alpha j conjugate, t u I u j. All right, so what do we have here? Well, that's pretty interesting because we can simplify this even more. This is alpha I, alpha j conjugate I j, inner product of lambda, eigenvalue lambda, and which is I u j, which equals to, we can factor out our lambda, which is going to be lambda, and then alpha I, alpha j conjugate I j, inner product ui uj. And since this is given that this is orthonormal basis, this is equivalent to lambda I, alpha j conjugate, and here it is, the Kronecker symbols. The Kronecker symbol is here. Then we can rewrite this expression as the sum of I, which equals j, and lambda I, alpha square, because this is the property of the complex numbers, and the Kronecker symbol, which equals to 1. Otherwise, it equals to 0, and these terms, they're just, annihilated. So this is the expression that we end up having, but the only missing part is that this is not actually the eigenvalue lambda I. This is the square root of I. Square root of lambda I. Here it is. So we can see that square root of lambda I is always it is always non-negative. Same applies for alpha scalar multiplier. It is always non-negative. And then therefore our inner product is also always non-negative for any vector belonging to the inner product space, which means that our t is positive. It kind of self-implies that it is also self-adjoint, but not only because it is positive, it is also, diagonal, and it is self-adjoint. That being said, it is kind of symmetrical in case of real matrices, or it is Hermitian, I guess. In case of complex numbers, it is kind of the transpose of its conjugate matrix. It is the original matrix T. It is Hermitian matrix, right? Okay, so with that being said, what is left to prove here is the uniqueness. No, actually, before proving uniqueness, we have to prove that t square equals p, because this is not something that was given by default. This is something that we have to prove. So in order to prove that, well, that's pretty simple actually, because t square is, well, let's say t square x. This is t of tx, which is t by definition of lambda square root of lambda ix. we can say xi, well, it doesn't matter, which is, lambda I tx, which is the same as lambda I square root of lambda I square root of x, which equals to square root of lambda I square x, which is lambda I x, which is the same as bx for any x belonging to space, and consequently t square is the same as p because they agree on the basis, and they agree on not only on a basis, but they will agree on any vector from the space because they agree on the basis. And any vector in the space can be decomposed as the vectors from this basis. So these two operators, they are identical. Right. Cool. So what is left is to prove the uniqueness between two, for this t square operator, how to prove the uniqueness. So that's a little bit tricky. First of all, we need to assume that there is some sort of operator, let's call it operator S. And this operator S is also positive. Not only is it positive, but it is also the square of this operator equals p. Well, that's enough for now, that's enough. But let's actually show the very interesting property here. If we try to find the S times p, we can see this as S square, which is S cubed, which is essentially S square S. This is the known property of matrices, which equals p S. Nice. That means they are commuting. They commute. Cool. So that means that SPX equals to S lambda I x, right? Which is lambda I Sx. Lambda I Sx. But we can also say that SPX, it is the same as PSX. And that equals to lambda I Sx. That means that Sx belongs to eigenspace of I if x belongs to eigenspace of I. So it preserves, the linear operator S preserves the eigenspace under the theme of eigenvector. That's amazing. And now, given that, we can show that, let's consider two cases. The first case is when lambda is equal to 0. If that equals 0, then apparently S px equals to 0. And if our S equals to square root of I lambda x, it kind of checks out, right? That kind of checks out. It holds. Because now x equals, which is equivalent to say x equals 0. Because this happens for any x. And that equals 0. All right, that holds. The second case is more interesting. Let's consider the S square x, because px is this S square x as square root of lambda square x, which is true by definition. And then we have, which is the equivalent to saying S square minus lambda I square root square of x equals 0 for any x. Then S square minus, here it is, the identity matrix. Don't forget about this. Identity matrix here equals 0. And then that means S minus square root of I identity matrix, and then S plus square root of I identity matrix equals 0. This is pretty interesting. Let's assume that this operator, or which one? Not this one operator. Let's assume that this one is non-singular, singular. That means its kernel is not equal to 0. Let's assume that. What will happen? Well, in that case, there exists some vector v such that SV equals minus square root of lambda v, and consequently the inner product of SV and v equals square root of minus lambda e, inner product of v and v, which is the minus square root of lambda I times second norm of v, which is always non-negative, which means it is non-positive. But this is not possible because it was given that S is positive. It is contradiction. It is contradiction. That means that this kernel is actually 0. That means that this operator is non-singular. And so what does that give us? The fact that this operator is non-singular. That means that the only possible way for this operator to annihilate is for v, or for any arbitrary vector, to be equal to 0. And from this follows that S minus square root of I identity matrix equals 0, which means therefore S x equals square root of I x for any x belonging to v. And we can see that this is essentially S means that S equals t. Well, because they agree on every operator I, which means that our t is unique. And that's basically the proof behind this problem, behind this theorem, where we proved that t is unique and positive, and the only positive unique operator. Here it is. Here's the whole proof for this problem.